Okay, and welcome to chapter 4. So we're now looking at bivariate random variables. So we're going to have two random variables at the same time, and we're looking at, is there a dependency between them? Is there a relationship? How do we take that into account in our bivariate distribution? So we'll start as before with random variables with the discrete case. So here's a motivating example. We'll come back to this later at the end of this chapter. So we've got the joint probability of two or more events that arise naturally in main experiments and on the consideration of nature, and therefore we were interested especially the relationship between them. So let's set up some notation. We're going to start in this case by having two random variables which will denote y1 and y2. We're going to start and assume they're discrete, real valued, and they each have their own state spaces. And we're going to describe a thing called the joint probability mass function, or joint PMF. We'll denote that as f y1 y2, and basically it is the probability that y1 equals y1 and y2 equals y2. So we're using comma here to indicate and. So here it is in actual set notation, just to recap that. But basically we're replacing the and symbol there with just a comma to make it a lot easier to write. So let's think of an example. We're going to toss a coin 3 times, and we're going to measure two random variables on that. First of all, the first random variable y1 will be the number of heads on the first 2 coins, and y2 will be the total number of tails, and we want to get a joint probability mass function. And we're going to do this as a table. But to start off with, what we're going to do is we're just going to think about our sample space. So our sample space in this case, well, you could have head, head, head. That's the first possibility. And altogether we're going to have 8 possibilities. So here's our 8. And here's going to be head, head, tail. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. So let's think about y1. So if we remind ourselves what y1 is, it is the total number of heads on the first 2 coins. So here we have 2 heads, 1, 1, 1, 1, 0, and 0. And y2. So again, let's go back. y2 is the total number of tails. So we've got 0, 1, 1, 2, 1, 2, 2, 3. We're going to put that together in a table. So let's think about our table. So we could have y1 on this axis, and the possible values y1 can take are 0, 1, and 2. And then we can have our y2, and that can take the values 0, 1, 2, and 3. So this entry here is going to be the probability that y1 equals 0 and y2 equals 0. Well, that doesn't occur at all. So that first probability is going to be 0. In fact, let's focus on the y1 equals 0 case. So we have 2 possibilities here. One of the times you have a 0 and a 2. So first of all, notice there's no 0, 1. You can't have a 0, 1 at the same time, so that must be 0. 1 out of the 8 possible, and all these, it's a fair coin, are equally likely. So each of these rows has a probability of 1/8. So in this case, we have that you could have a 0 and a 2 once, so that's a probability of 1/8, and a 0 and 3, 1/8. Okay, let's now focus on the ones. Well, a 1 and a 0 never occurs. We have a 1 and a 2, we have this row here and this row here. So this one has 2/8. We've got a 1 and a 1, 2/8. And then finally, you can't get a 0 and a 3. And the final 2, we just have an 1/8, an 1/8, 0, and 0. So there's our joint probability mass function. Okay. It's still a probability mass function. Okay, we've got two variables, still probability mass function. So in that table, all the entries should be basically greater than or equal to 0. So quick check. Yes, they're all zeros or an eighth or 2/8, that's fine. And if you add up all possibilities of the values, you should get 1. So if we add up this, we've got 0, 0, an eighth, 2/8, 2/8, an eighth, an eighth. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 8, so that comes to 1. So it's still a valid probability mass function. Sometimes though, we're not interested in both y1 and y2. We might only be interested in y1. And basically what we can do is we can use the law of total probability to get this new probability mass function. Now, often we will denote this as f of 1 y1. And that's just indicating that we're interested in the marginal distribution of the first random variable. And here we've used the subscript 2 to indicate the second random variable. And all we're going to do is we're going to calculate using the law of total probability. Now, to help you visualize this, I've got an extra video you can watch after this one, which shows a visualization of what we're actually doing. But let's look at an example. We've got the same setup as before, but what we're going to do now is we're going to work out the marginal distribution of y1. So we're going to say, what's our y1? And there's the actual answer, but let's show how we calculate that. So first of all, to remind you, let's have a look. Let's draw up our bivariate probability mass function. So we've got 0, 1, 2. We've got our y2, which is 0, 1, 2, and 3. And we had 0, 0, an eighth, 0, 2/8, an eighth, an eighth, 2/8, 0, an eighth, 0, 0. So let's imagine we wanted to first of all get the probability that y1 equals 0. Well, I see you can use the law of total probability. That's the probability that y1 equals 0 and y2 equals 0, plus the probability that y1 equals 0, y2 equals 1, plus dot dot dot, plus the probability that y1 equals 0 and y2 equals 3. If we go down and we substitute that all in, you will see that that's going to be 0 plus 0 plus an eighth plus an eighth, which is 2/8. But to some extent, if you go back to this diagram and think about what we just did then, this first point here is y1 equals 0 and y2 equals 0. This one is y1 equals 0, y2 equals 1. This is y. So all we were really doing was just adding down this column. And that gave us our 2/8. The same if you did the calculation and now looked at the next one, we would just add down this column, and this would give us the probability y1 equals 1 equals 4/8, and finally the probability that y1 equals 2 is 2/8. The nice thing is this is still a valid probability mass function. Notice these values add to 1, and they all lie between 0 and 1. In fact, in the next slide, we then say, well, let's do the marginal of y2. Well, if you did the same logic, if you wanted, for example, the probability that y2 equals 0, that'd be the probability that y2 equals 0 and y1 equals 0, plus the probability that y2 equals 0, y1 equals 1, plus the probability that y2 equals 0, y1 equals 2. They're all possibles. And that would basically be 0 plus 0 plus an eighth. Because if you think about it, it's the same logic. We're taking this number, adding this number, add this number. We're adding across the rows, so we get an eighth, 3/8, 3/8, and 1/8. And now you see why they call a marginal distribution, because to some extent we are pushing the probability down to the margins. So this gives us our probability mass function of y1, and this gives us our marginal probability function of y2. And all we're doing is we are putting all that probability on the margins. As I say, there's another video to visualize this for you as well. We could also get a conditional probability distribution. We can actually say, what's the probability that y1 equals some value given you know y2? So what's that relationship between them? Well, the nice thing is, this is just, if we look at this, we want the probability that y1 equals y1 given y2 equals y2. So we're going to think about all possible combinations. But by conditioning rule, we can write that as the joint probability mass function divided by the marginal probability mass function. So we're going to toss our coin 3 times and let y1 be the number of heads on the first 2 coins and y2. So we want to condition on y2 equaling y2. Well, again, let's go back and quickly draw up our probability mass function. So we've got our y1, 0, 1, 2. We've got our y2, 0, 1, 2, 3. We had our 0, 0, 8, 0, 2 eighths, 1 8th, 1 8th, 2 eighths, 0, 1 8th, 0, 0. And we want to say, what's the probability that y1 equals certain values given y2 equals, for example, 0. So what we do is we calculate our marginals. So this is an 1/8, 3/8, 3/8, and an 1/8. And what we're going to do is we are going to take every single entry and divide it by the marginal distribution of y2. So for example, here's our y1, 0, 1, 2, here's our y2, 0, 1, 2, 3. And you can ask the question, if I've observed it and I know that y2 equals 0, what's the probability that y1? So that has to be 0. We know the probability that y1 equals 0 given y2 equals 0 has to be 0. And how did I get that number? I basically took this and I divided it by this. So the next one is going to be 0 divided by 1/8 is 0, and finally 1/8 divided by 1/8 is 1. If you think about it, if I come along and I said to you, I've tossed these 3 coins, I know that y2 equals 0, so basically there it's no tails, and ask you what's the probability that the first 2 are heads. If there's no tails, they must all be heads, so the first 2 must all be heads, so it must be the 2. Again, we can continue on with this. We can now do the 0 divided by 3/8, that's 0. 2/8 divided by 3/8 is 2/3. And 1/3. We've got 1/3, 2/3, 0, 1, 0, 0. Notice each row of this is a valid probability mass function. Just because it's conditioned, it's still a probability mass function. You've just got this extra information, you've locked it in, and you have a new probability mass function. Now we could do the opposite way. We could condition on y1. So, again, we will go back. We will draw up our y1, which is 0, 1, 2. Our y2, 0, 1, 2, 3. Put in the values 0, 0, and 1/8. 0, 2 eighths, 1/8. 1/8. 2 eighths, 0. 1/8, 0, 0. And this time we're going to say, well, we've observed y1. So we're going to have to divide by the marginal y1. So let's get the marginal. That's 2 eighths, 4 eighths, 2/8. And now we're going to get our conditional. So this is all going to be the probability that y2 equals some value given y1 equals y1. Obviously this is not going to be exactly the same as the previous one. We've swapped the conditioning. So we've got a 0, 1, 2. This is our y1. We've got 0, 1, 2, 3. This is our y2. So this entry here is going to be the probability that y2 equals 0 given that y1 equals 1. Well, that just can't occur. So that must be 0. How did I get that? I took this number here and I divided it by this. Next one, we can go 0 divided by 4x. Well, actually, let's go down the y1. Let's condition on y1 equals 0. So we've got a 0, a 0, a 1/8 divided by 2/8 is a half and a half. Let's go down this. And again, to get this number, I take the 0 and I divide it by the 4/8 because I'm margining on that. So I've got 0, a half, 0, and finally a half, 0, 0. And again, notice that each of these now columns is a valid probability mass function. So there we've got it. We've got a bivariate distribution, which gives us the joint probability of y1 and y2. We can push all the probability to the margins and get our margins. So we could just look at y1 on its own or y2 on its own. Or we could also get the conditioning one. Using the conditioning, we also say, well, what's the probability that y1 equals some value, given we know that y2 equals, for example, 2. All these marginals, conditionals are all valid probability mass functions. So the values lie between 0 and 1. And again, they add up to 1. As I said, there's another video that accompanies this that shows a visualization of marginalization. I highly recommend you have a look at that. And next time we will look at a classic example of a discrete multivariate distribution, which is called the multinomial distribution. See you next time.